it is already given that H is a non-empty subset of G. Thus, it remains to show that H itself is a group under binary operation of G. Now remember, in order to prove H itself is a group, first of all we need to show H is non-empty, right? Because what does the definition of group say? A non-empty set G together with binary operation is said to be a group if so and so properties are satisfied. Now it is already given that H is non-empty, so that part is done. Now we are supposed to prove that the binary operation of G is actually a binary operation of H. In other words, we have to show, take any two elements of H, A and B, and we have to show that A multiplied by B belongs to H. But this part we will do at last. So we will directly jump towards the properties. So what is the first property of group? That is associativity. So first of all we will show that elements of H are associative. As we know, in order to prove associativity, we will need some elements of H. So I will say let A, B and C belongs to H be any elements. But elements of H are nothing but elements of G. Why? Because H is a subset of G. And we already know that elements of G satisfy associative property, and therefore elements of H will also satisfy the associative property. Thus, since we mentioned G is a group, for all ABC belongs to G. Now we are supposed to show that identity exists in H, right? So that is the second property of group. So I will say existence of identity. So what does the property say? Here the properties say there should exist E belongs to G such that AE will be equal to A, which will be equal to EA for all A belongs to G. But remember, here we are proving H is a group. So we should prove there exists E belongs to H such that AE is equal to A, which is equal to EA for all A belongs to H, right? Now see, in order to prove it, what is given to us? This condition. So we have to use that fact. Together we also have H is non-empty. Now what is the meaning of H is non-empty? There always will be at least one element in H, right? Therefore it is called as non-empty. So I will say as H is non-empty, there exists A belongs to H. Now since we are having some element of H, we can use this fact and the property to show E is in H. How? We will just write this A two times. So as A comma A belongs to H now, right? So what it will imply? It will imply that A into A inverse belongs to H, because what do we have here? AB belongs to H is implying AB inverse also lies in H. So that fact we have used. But what is A into A inverse? We already know that it is the identity element. Therefore, there exists E belongs to H such that AE is equal to A, which is equal to EA for all A belongs to H, and that is what we wanted to prove. Now we will move towards the next property, that is nothing but existence of inverse. Now what does the existence of inverse property say? For each A belongs to G, there should exist A inverse belongs to G such that A into A inverse should be E, which is equal to A inverse A. So here let us start with the element of H, let us call it as A. So we have to find such an element A inverse such that the multiplication of A and A inverse is E, which is further equal to A inverse into A. So I will say let A belongs to H. Now, since A is a member of H and in the previous property we have shown one more member is in H, that is nothing but E. So we are going to use these two facts to show that A inverse lies in H. Remember, A is the element of H and H is a subset of G. So A is the element of G. So inverse of A already exists but in G, right? As G is a group. So here just we have to prove that A inverse lies in H. So what I will say here? Here what do we have? E comma A belongs to H. Now again by using this, AB belongs to H is implying AB inverse is also in H. So this will imply A inverse is also in H, and that is nothing but A inverse belongs to H. So therefore what we have shown, therefore for each A belongs to H, there exists this A inverse belongs to H such that A into A inverse is E, which is further equal to A inverse into A. Now it remains to show that the binary operation in G is also a binary operation in H, right? Remember, that part is left. So in order to prove it, we should start with two elements of H. We are going to call it as AB, and we are going to show that A dot B is also in H. So here I have taken two elements of H, but note, since B is an element of H, where will be B inverse? What we have proved in existence of inverse property, if A is in H, then A inverse is also in H, right? So therefore we will have this B inverse is in H. Remember, we will also have A inverse is in H, but we don't need that. Why? Because what is given to us, that we have to use, right? What is given? If AB are in H, then AB inverse lies in H, and you can see that this inverse we are having for an element B. Thus, we are using the fact that B inverse lies in H. So we will say here as B is a member of H, therefore B inverse is also in H. You can say this is using 3, that is the existence of inverse property. Now here what do we have is, we have A is already a member of H, remember. Now we have shown B inverse is also a member of H. So what it will imply? It will imply that this A B inverse whole inverse will be a element of H again. From where does it come? It comes from here. If AB are from H, then A B inverse is also in H. So A B inverse are in H, therefore A B inverse whole inverse will be in H, which implies AB is a member of H, since remember this B inverse is actually B. So laws of indices do hold in group theory, so that fact we have used here, and that is exactly what we wanted to prove. So we have shown that H is non-empty set together with binary operation. So binary operation in G is also a binary operation in H, and we have also shown that the elements of H are associative, existence of identity and existence of inverse. So what we will say, let us call it as 4, right? Therefore H itself is a group under binary operation of G, and therefore H is actually a subgroup of G. That is exactly what we wanted to prove.